when the sun isn't shining, the wind's not blowing, at least one of the technologies will be working. And this is where the work on smaller microgrids, etc., for these isolated coastal communities, island states, etc., is really starting to gain some traction. If you're relying on one of other, then you're going to have diesel gensets there. And that goes against really where we want to be longer term with our emission reductions and cost reduction as well.
Hi, I'm Cray with the International Water Training Institute on behalf of the Australian Water School. Welcome to today's webinar on ocean energy. Today's webinar is sponsored by our friends at Flow3D, who have been part of many of our previous webinars. We're going to see some examples of Flow3D ocean energy applications toward the end of today's webinar. But first, let's welcome all of our attendees from all around the world. Thanks so much for your interest and your participation in these industry forums. Today, we hope you gain some valuable insights into the topic. In this case, these are insights that I think can help us be better stewards of the planet. And we also may see some opportunities to apply our collective knowledge toward tackling some of the current limitations around harnessing ocean energy. Now, let's hear from our presenters and panelists. I'd like to know a little bit about your current role, how long you've been involved in ocean energy, and maybe for today, just let us know how far you are right now from the ocean, from wherever you're coming to us from today. Let's go in the order we see it there on the screen. Michael, let's hear from you. Where are you coming to us from today and how long you've been doing what you do?
Thanks, Craig. Well, I'm down in beautiful Western Victoria in a little place called Hamilton. I'm about an hour from the ocean. But I've been involved with ocean energy for just over 9 years now, and kind of grew up working as an engineer in the oil and gas industry offshore, and have been doing that for probably about 20 years. So my background is a chemical engineer, and then went back and did a marketing degree as well.
Awesome. All right. Well, let's see if we can hear a little bit of marketing for ocean energy today. Larissa, over to you. Same questions.
So I'm on the Gold Coast, not very far from the ocean, thankfully. I'm an environmental engineer and part of the Met Ocean Science and Technology team here at RPS. And I first started working on ocean renewable energies in 2018 when I started my PhD, which was focused on tidal energy. So most of my experience on ocean renewable energies is on the collection and analysis of field data collected in prospective tidal energy sites here in Australia and a little bit in Europe as well.
Sounds good. Okay, and Ebony, over to you.
Hi, everybody. Thanks for having me today. I am actually very far away from the ocean, unfortunately. I live in a little town called Mount Beauty, which is the Victorian High Country. So right at the base of the Falls Creek ski resorts. Not that I'm not an ocean person myself. I did grow up in Queensland, in Noosa specifically. So I grew up around the ocean, but I just happen to live in the mountains now. So I'm a senior manager at Deloitte. I have been with Deloitte for about 7 years. I work in the climate engineering and the emission solutions team. And I'm responsible for leading the nature-based solutions and ocean energy portfolio of work. And that includes offshore wind, wave, tidal, and hybrid ocean energy microgrids. So I have about 17 years of experience in the technology space and have been focusing predominantly on the ocean energy space only for the last 12 months or so.
Excellent. Well, we're looking forward to getting your insights today. Today's webinar is actually the latest in a whole series of coastal applications that we've done. Let's have a look at the poll results and see, kind of compared to the other technologies that we've got, what everybody's background is. We've got a good mix between academic is actually a lot higher than normal today. Government and commercial are generally competing with each other for the top spot there. But what we really want to know is, what do you think are the top obstacles to ocean energy? And it's really been a close run there, but yeah, the technology has come out on top in that one. And it does look like most people are expecting the uptake of ocean energy to increase. And then looks like most of our attendees have not undertaken any modeling. You'll see some modeling results here. Tune in on some of our previous webinars. We covered in our previous one modeling waves and tides. We've also just covered offshore wind, and then we'll wrap up the year with desalination, which is often also in the coastal zone. So we've got a little bit of a coastal focus for these last couple of webinars. So Michael, while you start sharing your screen, I guess first, any comments from you about the poll results? Any surprises there?
No surprises there. Ocean energy is at different phases around the world, and a lot of that is dependent upon where government support is sitting and then market acceptance of the technologies. Thanks, Craig. And yeah, thank you everyone for having me here today. I'm here talking about our Azura wave energy and Azura ocean technology that we've been developing for 15 plus years. It's a challenging environment to play in. We're a little bit different to a lot of the others in the game globally in that we've all come out of the offshore oil and gas area. So we understand the harsh environment, the robustness that we require to operate in those environments. We're used to designing for 20, 25-year plus lifespans. So having those that background plus our parent company, we're heavily into very specialized hydraulic engineering, etc. We have taken our concept and built from there using our combined knowledge. We can see this is a growing demand. We know that within the renewable energy space, we've got wind, we've got solar, we've got all the other emerging hydrogens, etc., etc. Hydrogen, of course, being a stored energy rather than an energy source in itself. We could see that we needed something else to add to the mix, and we know globally the amount of potential energy in the ocean, be it waves or be it tidal, is phenomenal. How do we harness it? How do we harness it long term? How do we harness it economically so that it is commercially viable? These were all the questions playing around, and we started off by developing prototypes. Now we thought we're not going to just go straight into small, nice little calm areas to play with. We were off the coast of New Zealand, and anyone familiar with the New Zealand coastline knows that it is very rugged. We have very large and stormy conditions we've got to play with. So this was again developing our robustness, etc., of the technologies. And I can tell you, we went through quite a number of prototypes to get to a point where we were comfortable to then take our technology forward. We actually took our technology to Oregon State University, and utilized the wave testing facilities there, which was great, gave us a lot of information. Now, for us, one of the other barriers was localized acceptance and support. Australian government, New Zealand government, bit lukewarm, and at that stage, we'd had a few, well, not us, but the industry itself had a few misses in public perception on ocean energy, i.e. there were a few boat anchors sitting out there that hadn't worked or even sunk on the way to their deployment sites. We ended up being fortunate in working with the US Department of Energy, US Navy, etc. And over 2 18-month periods, we had full deployments at what is called the Wave Energy Testing Site, or WETS, in Hawaii. And these deployments were fully monitored by a third party in the University of Hawaii. So it allowed us to develop verified data and continue that development for that second 18-month deployment. Now, I can say during our deployments, we got hit with some very big hurricanes. So we were still producing through 7.5 and 8 meter waves, and the systems just work nicely. So how does it work? The system itself floats. So we have 3 mooring points that are tethered to the ocean floor. Again, these points can then be moved, etc. One of our key drivers is to, when our deployment has finished, be it 20, 25 years, etc., we can pull everything up and you won't know we've been there. So doing minimal environmental impact is one of our key drivers, as is recyclability. Now, we've all heard the negatives around wind and solar as far as recyclability of their componentry. So we're currently sitting at around about 92% recyclability of our complete system. That is one of our main drivers and one of the things we've charged our engineering team to compete with. So what you're looking at is a system that actually is picking up energy from 2 planes. So we're not only getting the waves, which is what the float is doing, and the float can actually go through a full 360 motion. So that helps it during very high wave conditions in a survivability mode. But it's also picking up the heave. So at the bottom of the system there, you'll see a larger component, and that's the heave plate. So that we're actually picking up from waves and also the heave of the ocean. What that has enabled us to do is really improve our capacity factor. Now, with wind and solar, capacity factors can vary. Solar in the 20s and wind now in the 40s. We're currently sitting conservatively at around about 50-51% capacity factor, which is pretty impressive. Now, we do that by really designing and optimizing for deployment sites. So it's horses for courses. No two sites are the same. This is where we rely heavily on modeling and physical data for each particular site, when we normally need that over a 12-month sort of running period or greater. The tethering points, again, allow us to pivot the system. So we normally have about a 30-degree pivot available to us. So that allows the system itself to optimize depending on wave direction, etc. So that's a key component for us. You'll notice there also we've got multiple struts going across through the center. This was a bit of one of those engineering points where we're developing our systems. We have 250, 500 kilowatt, 1 megawatt systems. They're really big, really heavy, and also very expensive. So a couple of Christmas breaks ago, we all kind of went away with the idea, let's take that step back and analyze. And we came back saying, why are we taking on grid? Grid scale is not where we are at the moment. We need to take on and be really, really good in the niches. And this is where we looked at how can we improve and burn down our cost. So we went back and we've actually worked on commercially available pipe. So by then integrating into the system, we were able to pull almost 50% out of our overall fabrication cost. That's huge. So all of a sudden that brought our LCOEs, everything down. But it also enabled us to remove one of the other major barriers, which was the logistics of getting equipment to the deployment sites. So by doing this, we actually now made the systems modular. So we can actually put these in containers and ship them anywhere in the world. So again, this brought down cost. It then enables us to put them on the back of ships, etc. So one of our other key points is we want these systems to be available for natural disasters, etc., and be relatively quickly deployable. Because not only do we do energy, and this is the clincher, we can also do water. So we took a step back during this time. We thought, hang on, we've got some spare real estate here in our systems. How can we improve? And what we did was reimagined commercial RO. So rather than being electrically driven, it's now mechanically driven. And in doing so, we've increased efficiency by over 10%. So with our systems now, what we can do is energy or water or a combination of both, which then really opens up to the markets, what is available. Again, we haven't reinvented the wheel. We've taken existing and proven technologies that is very robust and just reimagined it, made it more efficient in the way we're doing. So we now have potential water systems for potable water or agricultural grade water to now be emissions free in its production. So again, where are we currently sitting? We've got 50 kilowatt, 100 kilowatt, 250, 500 kilowatt units. But is that where we're heading? In our water, we've got 50,000 litre per day and 100,000 litre a day systems. Again, everything that we're doing is it's modular, but it's also variable in what we can actually do. We will optimize for the site and what the application is. Per se, we are currently working on systems that are actually fixed, and these will be fixed against offshore potential oil and gas platforms that will provide energy for these unmanned sites. So again, we're putting renewable energy sources to power offshore oil and gas sites or underwater recharging stations for UUVs, etc. So this has been a hell of a challenge. It's been an engineering challenge, robust versus economically stable. And we've had to pull back a number of times and go, this just not heading in the right direction. But with our multiple ocean energy deployments, and that's the key, multiple deployments in the ocean through tough conditions, we're now at that point where we have multiple patented technologies. We have utilized existing componentry. So nothing's really too crazy unique in its manufacture. And we're currently now in a commercialization stage. I know it's hard to believe for those of you in Australia and New Zealand, but as against Europe, which has been forging ahead and pouring a lot of money into ocean energy in both tidal and wave, we are actually now moving forward. It's taken a lot of work and an awful lot of money, and all that money hasn't come from government sources. So we're excited about the future, but we've also got to remember our place at the moment. We kind of think of ourselves as 10 years behind wind. All right. So we can see us ramping and developing. Now, the systems we currently have are really designed for the niches. So we're talking marine aquaculture, and we are working on those projects here in Australia and New Zealand. These are live commercial projects. Ocean observation, isolated communities and isolated utility areas, and offshore wind. Offshore wind, that's a weird one. Why would we want to be involved with them? Because it's about, the future is about a combination of technologies, not one particular technology. So in between offshore wind, you could have ocean energy systems. So when the wind isn't blowing, the waves are still there, the heave is still there. We can then extrapolate costs of these offshore projects with an increased energy efficient or energy production. So there is a real beginning of an understanding of how these things will merge together. We're seeing that more in Europe, where their offshore wind is far more mature than it is down in this part of the world. But we're just starting to have those conversations, and it makes a lot of sense. So when the sun isn't shining, the wind's not blowing, at least one of the technologies will be working. And this is where the work on smaller microgrids, etc., for these isolated coastal communities, island states, etc., is really starting to gain some traction. If you're relying on one of other, then you're going to have diesel gensets there. And that goes against really where we want to be longer term with our emission reductions and cost reduction as well. So if we look at offshore wind farms, again, these are some great graphs that came out of the Dutch Marine Energy Centre. We did some fantastic modelling on how it all goes together. And we can see there, solar is up and down, wind, a bit all over the place. But the one semi-consistent all the way through is wave. So we are seeing this gradual acceptance. We're really excited about where ocean, be it both wave and tidal, is going. And it is horses for courses. There are multiple technologies under development. Is our technology the answer? It's part of the answer, and it's going to be, dependent upon the deployment sites. There are sites where you have very few waves but great tidal, etc. So in the Mediterranean, when we've been working over there, we have to work and redesign to work with wind waves rather than the larger waves. And especially down in my part of the world, we have waves that we start at about 1.5 and go up to 7 to 8 meter waves during the winter months. So it really is horses for courses, and it's working as an industry that this will actually happen. But we're excited about what we can bring as far as energy and water. Water is going to be a key driver. As we have sea level rising, we have depletion of aquifers, etc. Saline levels are rising, and that will have impact on land, both on the continents, but also in the island states. So we believe this can offer a real alternative. And these are the other things this is the thing we've got to look at. It's not just energy, it's that energy being utilized to assist in a broader scope. So that's it in a nutshell. As I said to Craig, I could talk for hours and hours and hours and go into all sorts of detail on this, but I really wanted to give you a broad overview of where ocean energy is sitting and where we're sitting and the challenges we've overcome to get to where we are.
Okay, great. Well, thanks for that. We wanted to show everybody an application, a real world application, and again, highlight some of the challenges with it that are associated with it. So if you have questions for Michael about the technology, and he's very familiar with the industry as a whole and some of the other competing sources for energy and ocean energy, we could do geothermal, we could do wind, we could do waves, we can do tides. We're going to hear next about tides. So Michael will be in the background answering questions while Larissa comes on. Larissa, we're looking forward to hearing your presentation. We'll get a deep dive into some of the really heavy duty hydraulic analyses and physical modeling that goes into some of this. And you'll hopefully see some of the challenges, why it's not just straightforward. So much energy out there. Why aren't we using it? We'll have a panel discussion at the end. So over to you, Larissa. I can see your screen just fine.
Thank you very much, Craig. As I mentioned in the beginning, the work that I'm presenting today was part of my PhD research. So my PhD research was actually part of this bigger, broader project called Austin, which was concluded in 2021. And it came as a result between the collaboration between universities such as the University of Queensland, where I did my PhD, and the University of Tasmania, as well as industry partners, Tidal turbine developers, and the Australian Renewable Energy Agency. And the Austin project had this main goal to assess the potential and the feasibility for tidal stream energy generation in Australia. And for those who are not familiar with the term, tidal stream energy is the energy generated from tidal currents. So it looks a lot like wind turbines, except that they are underwater and they are moved by the tidal currents. So within our project, we had people looking into sediment transport dynamics, environmental impacts, economic feasibility, coupling tidal energy with other sources of energy, as well as Michael has touched on this topic as well. And my work specifically was focused on turbulence analysis in our study sites. So based on multi-criteria analysis that took into account not only the physical resource, but also socioeconomic aspects such as proximity to isolated communities, the Austin project has selected 2 sites as our study sites. The first one was Bank Strait, located in Tasmania, and the second one was Clarence Strait in the Northern Territory. And so these sites were also the study sites of my research. So just before I go ahead and tell you more about these locations, I'll go back to one of the main challenges that the tidal energy industry faces, which is again related to longevity of the devices. So for tidal energy to become commercially competitive against other sources of renewable energy, developers need these devices to endure this really harsh conditions for about 25 years. However, sites with good potential for tidal stream energy generation are often characterized by large waves, pronounced shear profiles, and high levels of turbulence, which are all factors that lead to large load fluctuations on the turbine blades, which can eventually lead to premature blade fatigue, something we definitely want to avoid. So because of that, it's important that we can collect data to properly characterize turbulence and wave climates at these sites so that tidal turbine developers can use this information to improve their numerical and physical models. However, there's still quite a few challenges for properly estimating turbulence. One of them is wave turbulence interaction, which is something I've looked into in a bit more detail during my PhD, and I'll talk about it. The fact that there are currently no international guidelines which discuss the estimation and measurement of turbulence parameters. And then finally, up until the beginning of my research, the lack of studies with long-term turbulence measurements actually available in the scientific literature. So going back to the guidelines, there are 2 main well-known guidelines for tidal energy resource assessment. The first one's given by the European Marine Energy Center. And this one, it gives clear instructions for wave and current characterization and data collection, but it doesn't really discuss turbulence at all. And then the second one is given by the International Electrotechnical Commission. And this one actually recognizes the importance of turbulence, but again, it doesn't give instructions on how these measurements should be taken, what's the minimum sampling frequency, how long the instruments should be in the water. And instead, it directs the reader to the scientific literature. These devices can have, depending on the technology, of course, they can have rotor diameters of nearly over 16 meters, which means they occupy a big part of the water column. And because of that, it's important that we get a good idea on what are the velocities and the turbulence levels across the entire water column. Because of that, the instrument of preference for data collection for tidal energy applications are the acoustic Doppler current profilers, or ADCPs, which are quite well known in the oceanographic community. And they are instruments that can give you information on the flow velocity across the entire water column. So they do have relatively low frequencies compared to other instruments, such as the ADVs, but they give this good benefit of looking at the entire water column. For my research, I used the Nortec Signature series, which is a relatively more modern technology, which allows for higher sampling frequencies. There was a good benefit for turbulence characterization. So taking all that into account, some of the goals of my PhD work were to go to these study sites, deploy different ADCPs so that we could have a good idea of the long-term variability of the resources, and also to assess the spatial variability of resources across the channels. I've also looked into wave climates and characterized turbulence parameters. I've had a chance to test, develop, and compare different wave turbulence decomposition techniques. And for that, I used the few data, but I've also done some laboratory experiments in a towing tank. And then finally, I did a little bit of numerical modeling to look at how a turbine would perform under the conditions that I measured in the field, so using the field data again. So going back to the study sites, Bank Strait, which was our first site, is located northeast Tasmania. And it's this one single wide channel, about 16 kilometers wide. Depth ranges mostly between 25 and 60 meters with some deeper areas. And the maximum current speeds reach 2.3 meters per second. Now, the wave climates there were quite challenging, which is not only challenging for the devices, but it's also difficult for us to go then to collect this data. So we had mean wave periods ranging from 7 to 12 seconds, so quite long, and maximum significant wave heights overcoming 5 meters. And then our second site was Clarence Strait. It's just off the coast of Darwin. And Clarence Strait is quite different. It's actually formed by several narrow channels separated by the Vernon Islands. The depth there varies mostly between 20 and 40 meters with some deep pockets, and maximum current speeds were a bit faster, which is good. So reaching 2.8 meters per second. The wave climates were also more gentle. So we had shorter waves with mean wave periods of 2 to 3 seconds, and wave heights very rarely overcoming 1 meter. So I've mentioned wave turbulence interaction and decomposition a couple of times, but I haven't really explained what it is. So in the presence of long surface gravity waves, we have the wave-induced orbital velocities essentially being superimposed to the turbulent velocity fluctuations. And if we look at this data, that's essentially a sum of orbital velocities and turbulence, and we did a spectral analysis of that, we would end up with something along the lines of what I'm showing here. So we would have a pronounced peak in the energy spectra in the same frequencies that we have waves. And if I moved on and estimated turbulence with the data like that, I would very likely end up with an overestimation of turbulence parameters, which would eventually lead to inaccurate modeling and possibly over-engineering. So what we need to do is to decompose wave and turbulence. However, even though the story may sound quite straightforward, putting that into practice can be quite tricky. And that's because we have the orbital velocities occurring in the same frequency as large turbulent eddies. So it's not as simple as just applying a stop-in filter, although I've tried. So I found that this was a strong and constant characteristic of Bank Strait because we had those long waves. And so I had to spend some time testing and investigating different methods because this is not at all discussed in the guidelines. So I've tested different techniques, again, not only using field data, but also some laboratory data. And I found that the one that works best for me is a signal processing technique called synchro-squeezing wavelet transform. And later on, this method was also applied in other sites in Europe. So even though there was still some room for development, it was the method that worked the best. So just so you have a bit of an idea here, we have some results. And the last one are the spectrum generated from the SWT technique. So there was still a bit of a drop in the spectrum, which is something that we don't want, we want to avoid, but it was the best one compared to the other techniques. So after that, I moved on to actually estimating turbulence parameters. So after collecting the data in the field, I had data sets of 2 to 3 months long with sampling rates of 4 to 8 hertz, which are relatively high sampling frequencies for ADCPs. I've applied the SWT methods to data from Bank Strait. I've also looked into wave climates and mean currents. And then I estimated parameters like turbulence intensity, turbulent kinetic energy, production and dissipation rates, and integral length scales, with turbulence intensity and integral length scales being the most discussed parameters by the tidal energy community. And for those who are not familiar, integral length scales, we can sort of think of them as the larger scales of turbulent eddies. So they're quite energetic. I've also looked into how these parameters varied with the stage of the tidal cycle and with wave climates. And what I found here was that turbulence was not that sensitive to wave climates, but it was quite sensitive to the stage of the tidal cycle. And that was very clear, especially in Clarence Strait. There was a very pronounced tidal asymmetry, and that's because of the presence of the Vernon Islands. So depending on if the tide was flood or ebb, then the islands would be in a different position relative to the flow, and that ended up having a big impact on the results. And then finally, I used a blade element momentum model, which is a method very much applied in the tidal energy industry, in the wind energy industry as well, to look into turbine performance using the data that I had collected in the field. So I looked into how the performance varied with changing hub submergence depth, so essentially where the turbine would be in the water column, in the presence of large waves, and also under different turbulence intensities and integral length scales as well. For this part of the work, one of the most interesting results came from the hub height variation investigation. So the main parameters that I was looking here were the standard deviations of power and thrust coefficients. And what I expect, which are values that are dependent on velocity. And what I expected to see was larger standard deviations when the device was closer to the sea surface, because it would be closer to the waves and where the orbital velocities are larger. But what I found was the opposite. The standard deviations were larger when the device was closer to the seabed. And that's because we can think that in the bottom half of the water column, we have a more pronounced vertical gradient of velocity. So we have much more shear. And that ended up having a bigger impact on the device. So just to sum it up, some of the outcomes of my research include testing different wave turbulence decomposition methods that had never been applied to tidal energy sites before. I've also quantified turbulence parameters in sites that, again, had never been explored before here in Australia. And these data sets are now publicly available. So I've provided the link for that publication, and it should be in the webinar website as well. So if you're interested in taking a look at the data or playing with it yourself, it's there. And finally, I've also investigated how a device would perform using the field data from sites that, again, had never been studied before. So yeah, that's what I had planned for today. Thank you very much. And if there are any questions that's for some reason we can't address today, please do feel free to get in touch.
Excellent. Well, thanks for that. That's fascinating stuff. We're going to post that this research up for you. Ebony and Michael, go ahead and turn your cameras on if you could. But yeah, I'm gonna any of the resources that we discussed that we want to put out there. I've got a website I set up for the previous one on offshore wind, and I'm just going to add these to the same one, hydroschool.org/marine. We'll put any research up there, any additional papers, any projects that are really cool, including that dissertation, which is available online. So with that, welcome to the panel. Welcome back, everybody. Ebony, I wanted to maybe start with you. And having just done this one on offshore wind, a webinar just like this with some experts on offshore wind and some of the challenges there, fascinating how, what it takes to get a wind turbine stable out in the ocean. It's an absolute engineering challenge and an environmental challenge as well. So somebody asked the question, why not do it together? Once you're, if you've got an offshore wind farm, why not also harness the wave energy or tide energy if you're out in the tidal area? Is that viable, feasible? Has that got its challenges? What do you think, Ebony?
Definitely viable, definitely feasible. And I know that there are a number of different parties in Australia as well as globally that are looking into the feasibility of this and actually conducting some site trials. Mm-hmm. From what I understand, there's immense benefits of looking at co-location of wave energy with offshore wind farms, for example. You can have significantly reduced installation costs as well as operational and maintenance costs because you're sharing the infrastructure and the space. And you have the opportunity to bring down the overall cost of energy. I'm certainly no expert in this in the space of co-location, but I do remember seeing a study just recently that talked about also the energy efficiency benefits and the reduced or levelized cost of energy, so a reduced LCOE over time when you have wind and wave co-located. Yeah, so definitely, I think with the opening of the new renewable energy zones in Australia and Victoria, in particular in the Gippsland area, I'm certainly aware of a number of companies that are looking into the feasibility of co-location of wave units, specifically with those offshore wind farms. Perhaps Michael might have some interesting thoughts on that as well.
Yeah, Michael, I saw your response on that question as well. So if we could hear from you on that. And in the background, Larissa, if you want to have a look at any of the other questions that might have come in, and we'll address a couple of those going forward. But yeah, Michael, over to you. Same question.
Thanks, Craig. And look, to echo Ebony's first point, they're definitely doable. There has been a lot of research done recently in the EU on combination of technologies. Now, whether that be having an ocean energy system interspaced between wind turbine deployment points, or again, looking at potentially integrating ocean energy systems into the offshore wind platform itself. Now, depends on what platforms and things they're going to utilize, but it will increase the overall generation capacity of a project, and also which then allows the amortization of that overall project cost over a greater energy supply capacity, utilizing very much the same infrastructure. Has this been done in practice yet? No. But it certainly, again, comes back to my point of, the future is about a combination of technologies. It's not one technology over anything else. So it makes sense to look at, can we combine this? And it's going to come back to which platforms are utilized depending on deployment site for the offshore wind, whether it be a full platform or whether it's just a tower. A lot of that's going to have to do with water depth, etc., as well for the offshore wind, whether it's going to be floating, who knows, or whether it will be seabed based. So I just answered one of the questions there. Again, with our fixed systems, it's something that could be added, but then if it's fixed, you're pretty much losing one of the energy planes, potential energy planes. So you're just coming down to purely a wave rather than the heave as well. And this could potentially work for a number of the other devices and technologies under development as well.
Yeah. No, and that's, it takes some creative thought. Maybe 10 years from now, we have another webinar like this, and there's something we haven't thought of yet. And, some of the things like having, I had never really thought about the combination of, ocean energy with desalination. Well, desalination plants tend to be near the ocean and they need a lot of power. Some of these things are no brainers. Okay, let's try and see what we can harness. None of them are the magic bullet, though. There's nothing that's going to solve any crises all by itself, but we certainly need a mix like that. Larissa, a quick question then for you, just in general. So we heard a lot about your academics and some of these heavy duty, robust studies on how the hydraulics works on this thing. But in the big picture, do you see with ocean energy, the idea with these, to get a return on your investment, they need to be out there for a long time. Is this, 10 years, let's make a prediction. 10 years from now, we'll get back together. We'll have an anniversary webinar here and see where we've come in the last 10 years. What's your prediction? Are we going to do a better job and have a bunch of these out there that are viable and that can last 25 years without falling apart in its tidal zones, harnessing everything that you said we can do? Is this pie in the sky, or 10 years from now, do you think that we'll all have that there'll be a bigger fraction of that pie taken up by tidal energy in particular?
No, I'll say I'm quite optimistic, especially because there are commercial projects in the world already. Here in Australia, at least as far as I'm concerned, we don't have commercial projects in place yet. But for instance, in the UK or in France, we have commercial projects that are predicted to expand and more turbines to be installed as well. Of course, these sites, they have higher velocity, so that's why they are more attractive to the developers. For instance, the sites that I've investigated here in Australia, we had current speeds reaching just under 3 meters per second, while in the UK or in France, we have channels with velocities of up to 5 meters per second. So that's a lot of energy. And it's quite attractive and quite promising, but it's still in its infancy. I think there's a lot of research, and the scientific community is quite interested in helping develop this technology as well. And yeah, so I hope that we're getting closer. I think we're getting closer.
Yeah, no, good. I think that's the case as well. So we'll see where we go from here. And today, I mean, generally we like to bring on some Australian experts, and we bring some international ones as well. Today, I'm actually coming to you from the US, so my accent finally matches my place of broadcast for this webinar. Usually, I'm coming at you from Perth, Western Australia, but today we've got a very high representation here in our technologies that we've been presenting, showing what Australia can offer to the rest of the world. And we are interested in promoting that through the Australian Water School, obviously, and seeing how we fit into the international picture here as well. Let's go back through in the same order again, and this time I'll just have you pick your favorite question or something that you've responded to, something that might have been upvoted. We'll go back through with in that same order. So if each of you could have a look at something you'd like to hit, and what we'll do in the background is run a bit of a slide reel here on some really cool applications for Flow3D. Now, they're the sponsor of today's webinar, and if you would like to do any of this yourself, sometimes now the way these physics models work, you can try all sorts of different things that you used to have to put a physical model together for. Maybe somebody out there wants to try this themselves and try some way of harnessing the energy and get some more efficiency out of it. We'll throw a few cool ideas up here. I love these animations and these graphics. And then, if you're interested in learning this yourself, come on board. I think next year we're going to be running some Flow 3D courses where you can actually, attend and figure out how to do this yourself, and then maybe test out your creative ideas and see how you do with it. So we'll have a couple of those slide reels running in the background just for discussion points. But while that's going, back over to you, Ebony, first, if you could have a look at any of the questions that have come in from the attendees, maybe choose one that you would like to address for yourself.
All right. There's an anonymous attendee who's posted a question here, which I feel is very valid and a very interesting one. So the question was, how does the wave energy available in the Australian coastal offshore environments compare to other ocean locations globally? I know certainly Michael and Larissa will have some thoughts on this, but it's my understanding that Australia has a really significant wave resource availability compared to other parts of the world, and that's due to our location and the easy proximity to the ocean. The areas particularly that seem to have the highest wave resources are the southeastern coastline, the southern coastline, and the southwestern coastline. And some of the estimates that I've seen around the potential wave energy capacity in Australia is anywhere up to about 2,000 terawatt hours per year. Michael and Larissa, you may have some additional thoughts to add on to that as well.
Yeah, so Michael, let's hear from you. And then if you wanted to hit another question after that, dive straight into it.
Thanks, Ebony. I think it's slightly more than 2,000 kilowatt hours for some of the areas.
I think I said terawatt hours.
Did you? I'm sorry.
Yes.
Yeah, 2,000 terawatt hours.
Difference.
That's on the ball. Yeah. Yeah. Look, in reference to that question, we have some of the best ocean energy, wave energy sites available with potential energy in the world. We also have, our continental plate does go out a fair way in a lot of areas. So we're not talking about having to deploy in really, really deep water. For example, our system needs a minimum of, say, 20 meters. Again, that can be variable. But in Australia, our biggest issue is our concentration around the coastal areas in the Melbourne, Sydneys, and all that of the world. So, I mean, where I am sitting here, if I look out my window towards the Grampians, which is a beautiful part of the world, within our region, we've got in excess of 1,500 wind turbines. So we're providing a lot of energy here in the regions that has to be shipped out to Melbourne. So it's whether we can utilize this amazing potential energy source and make it more localized. And this comes back to, Ebony, what we've talked about before, is in these smaller microgrids or grid areas for these, the coastal communities and that around the Australian coastline, Tasmania, or again, this goes into a lot of the offshore and deeper sea aquaculture sort of areas as well.
There was actually a question that was directly related just to the coastal question or the coastal comment you made there, Michael. Let me just quickly find it. It was from Ashneil Sharan. So the question was, how much would it cost to install wave energy for small island nations? So assume you would be talking about either a standalone unit or perhaps an integrated ocean energy microgrid of some sort.
Look, it's very much how long is a piece of string.
Yes, that was my answer as well, but I thought you may have something more sophisticated to add there.
Yeah, look, it's, as I said, no two sites are the same. It's one of those things we'd have to understand, one, the requirements of the site, and also to really look at the area. What are the depths? What are the wave profiles, etc. And then work around that to develop a conceptual plan for the project, and that would allow us then to give costing. So normally these things can be done, but it's a matter of really understanding. And when I looked at some of the Pacific islands, you've got to be relatively close to shore, which is fine. I'm all for reducing cable runs and those sort of things, but you kind of go off and all of a sudden you're down at depths of 2,000-3,000 meters. So that then becomes, from a mooring perspective, becomes very, very expensive And again, all this, as you pointed out initially, Ebony, is it pushes up the LCOE. In saying that, floating wind turbines would have the same problem. But we are finding amongst the island nations, etc., where land is very limited, there is pushback against onshore wind, and there is pushback against solar, purely for the ground it takes up, and also from a visual perspective, in its effect on potential tourism trade.
No, that makes a lot of sense. Larissa, I may be interrupting you. It says you're in the middle of typing the answer to this question, but I would be interested. What's the range of blade sizes that you've tested or that you've seen, and how close are we getting? Here we're seeing a bunch of numerical results. A lot of times they'll be calibrated against physical models. How are we doing in comparing physical modeling results with numerical modeling results, and over what range have you seen those tests applied?
So for my work specifically, I've only tested one diameter, and that's based on the turbine, one of the commercial turbines from the UK. And the diameter, if I recall well, was 16 meters. But there are lots of papers, especially on physical models as well, with the tests done on towing tanks, which are quite interesting too. There was another question here, and that's what I was thinking of before. Given the average wave speed and depending on tidal cycle, what's the optimum depth of the hub in the ocean to achieve optimum energy? And I think that's the magic answer, one of the magic answers that we would like to get. But I would say that can be quite site specific and also device specific too. So we have, I think the most well-known devices are bottom-mounted turbines that, as I mentioned before, they look just like wind turbines, except that they're underwater. But we also have floating turbines from barges and with different scales. So the one that I've used in my numerical model was based on the one from the UK with 16 meters diameter, but we have smaller turbines as well, which are designed for slower velocities. So yeah, I wish there was a magic single answer for this question that would solve lots of problems, but it's not that straightforward.
Yeah, no, perfect though. No, thanks for that insight. This will be a kind of a free-for-all question. I know when wind energy came up, even with offshore wind, maybe not as much of an issue, but some people are making the case that you are taking energy out of the system and you're actually changing wind patterns with your wind farm. Are you and with tidal influence, would you be changing like the arrival of a tidal bore? Probably not. With wave energy, somebody asked the question, does that, would you end up damping wave energy that would otherwise be reaching the beach? Anybody? That's a free-for-all question. Whoever wants to speak up first.
I can talk about tidal. I wouldn't say that it would make a huge difference, or at least not that I'm aware of, in the tidal velocity, generally speaking, but there is of course a difference within the tidal farm. So if you have a device that's in the wake of another device, that will definitely play a role on the power that you will be extracting. And that's why there's also a lot of effort into the optimizing the layouts of these farms as well. So
that makes sense. Yeah. On the hydraulic modeling, especially when you start getting even into streams, start putting the streams into or turbines into a stream, and you got to make sure the spacing is right. Otherwise, some of them are just very inefficient because they're in the shadow of the other one. Any other comments, Ebony, Michael?
I think there would be potentially benefits to having wave energy arrays located close to the shore. Because I do feel like, and perhaps Michael has some thoughts on this as well, but I feel like if you had an array, so multiple units located close together, there's the potential for them to absorb some of the energy from the waves that are located a little bit offshore, and therefore reduce the force of the waves as it meets the shore.
That makes sense. Michael, any thoughts on that?
I think logically that makes sense.
Yeah, Ebony, you're absolutely spot on. Even though it's minimal, there is a dampening effect. And if we can do anything, if we can create the energy whilst minimizing or reducing at least the erosive impact of waves along our shores, then that's potentially a positive impact. Again, there are various technologies in wave that are actually shore-based. They will become virtually sea walls as such. Um, but the offshore floating systems in an array would potentially dampen some of the waves. Be it we'd have to do a lot of modeling, and again, this would be a very site specific. Um, but it would take some of that energy out, which then would reduce down the erosive capacity. And as we know, as we're going to rising sea levels, etc., anything we can do to dampen down the effects. We've seen many things now where we've had large storm events in low-lying Pacific islands, and they're just awash with water. So if there's ways we can do stuff to potentially help, I think it's a win-win.
Yeah, well, what we can do now, we're just about out of time. Michael, just keep going on those thoughts. If you can just give us your final closing remarks, send us home with some messages. We'll go back in that backwards now. Michael, then Larissa, then Ebony. Give us your closing remarks for the day. We've got hundreds of water professionals watching this. What can we do to help further the science? What can we do to help make renewable energy like this more of a reality, and share more of a component of that overall energy pie that we've got? Michael, your final closing thoughts.
Well, I don't think wave energy and ocean energy is as far away as a lot of people think. We don't see a lot of it down in Australia, New Zealand. Europe definitely moving ahead. We just need people to talk about it more. It doesn't enter into especially in the public space, the government psyche, and we need it to be part of that future energy mix. So there are some great technologies out there. We just need to get on it and support them. There's a lot of research still to be done, a lot of modeling still to be done, as things will improve. But as I said initially, we see ourselves about 10 years behind wind. We just need to get stuff out there and get it going. As like with any sort of startup industry, mainly SMEs, so we're all burning through cash like no tomorrow. But it's a matter of we just need to get that step up, and it's very difficult when we're competing against the big conglomerates of wind and solar, and of course the hydrogen train, to get noticed at those public levels, to get the support that wind and solar got when they were kicking off.
Yeah, well, we're the water school. We're all about helping to further the science around water and do it in a safe and environmentally effective
and Craig,
way.
if I could just add to my point there, one of my key things is I really see huge potential in the water production side, as you to earlier. If we can have energy-free, emissions-free water production, be it aquifer replenishment or for drinking water, I think that's a huge thing.
Oh, we need to do a whole webinar on aquifer replenishment, because it's such a huge issue when it's been drawn down. How do you get it back in? And yeah, if you can harness that energy to help pump it back in, yes. I mean, these technologies, it's just amazing to think of, ideas that may not have been widespread a few years ago, taken hold, because necessity is the mother of invention, they say. So Larissa, over to you. Final closing remarks from you.
Yeah, sure. So I guess I'm with Michael in how we can support the development of ocean energies, talking more about it, organizing things such as this webinar so that we get more people involved and aware of where ocean energy stands in the world now. And with that, I would also like to make a recommendation. There's an organization called Ocean Energy Systems, and they release a report every year that gives a bit of a picture of what are the commercial and research projects on ocean energy around the world. So it's listed by country. And I find it a really nice way to keep updated, because it's very dynamic, right? We have things changing every year. So it's a really nice way to keep updated with on how ocean energy is developing around the world. So yeah,
Excellent.
if you're interested, make sure you check it out. I like this report very much.
Okay, well, we'll add that link to the, there's the link right there. Perfect. So we'll add that to the resources as well on the YouTube description, et cetera, and under hydroschool.org/marine. All right, Ebony, bring it home for us.
Thanks, everybody. Just some final closing thoughts from me in terms of what I think needs to happen over the next 10 years to support the growth of the industry. I think co-location of wave devices with the offshore wind industry is a huge opportunity, and I think that it's going to become even more significant as some of those wind farms start to become operational, particularly in Victoria to start with, in the Gippsland area. I think we can do a lot around collaboration. So firstly, learning from other global implementations of ocean energy around the world to help accelerate the sector and the understanding of the kind of challenges and opportunities in Australia. So I think we can certainly collaborate better at a global scale and apply some of those learnings in Australia. But I also think in terms of collaboration, there's a huge opportunity for the industry to actually work together. And by industry, I also mean, there are a lot of ocean energy technology companies out there, Azura being one of the more mature ones, certainly. But I do feel like there's a really big opportunity for these companies to all be working together to try to develop the opportunities and the growth of the sector rather than working independently or in silos. So I would love to see that happening more. And then just one final thought, I think there are still some challenges around the recyclability and the circularity of materials. Certainly in conversations that I have with a very diverse range of people, one of the questions that always comes up around renewable energies is, what happens to the wind turbine blades once they're at the end of their life? Do they still get buried in the ground? What happens to solar panels at the end of their life? And a lot of the materials are not recyclable. And I do get asked that question a lot when I talk about the ocean energy space. And the question that comes up is, how are the materials recycled? What's the kind of circularity life cycle of those materials? So I think there's a huge opportunity for growth and more research and development in that space. And I know, Michael, I think you mentioned in your presentation, was it 92% recyclability of your technology, which is amazing.
Currently at 92, I'm trying to get higher, but you kind of hit that nice little plateau. We're trying to push that up.
Yes, exactly. So I do feel like there's quite a bit of opportunity there as well.
Yeah, outstanding. And there's so many, it's multifaceted, and we hope we've brought you a little bit of a perspective, a spectrum of disciplines that all have to come together to help have this work out efficiently and safely. So with that, thanks so much to all the attendees everyone today from around the world, asking these questions, engaging with us. Thanks so much to the presenters and panelists coming on as volunteers, helping to further the science and the industry here and the technology, and do it in a safe and effective manner so that we can, all help make the planet a better place. You'll see a bunch of resources here on the slides that have been running for the last few minutes. Upcoming webinars, join us for those upcoming courses where you can get some training courses and doing some modeling yourself. And we look forward to further interactions with you. Thanks everyone for your attendance. We'll sign off for now, and we'll see you next time with the Australian Water School.